Let's see.
That sounds good. Okay.
Very good.
Yeah, so I was just saying, I know we're running behind on the talk schedule. So there's no way I'm going to be able to squeeze my talk into 10 minutes, but I will try to get us out by like 3.
No, don't feel like you have to compress it to 10 minutes or 15
No, well,
minutes.
it's not going to be 10 minutes, but I'll try to do 40.
Oh, okay, 40, 50.
Yeah. Okay, let's get this slideshow going. Okay. Oh, and I don't want it to progress automatically. Okay, cool. So welcome everybody. So this is going to be solving problems with topos theory. It's going to be on the Weil conjectures. And I ended up having to take out a lot of the topos theoretic stuff just because it's kind of technical and I like my talks to be approachable. And also I was struggling to find concrete examples for what the Weil conjectures are. It turns out they really say something super concrete, but when you just read about them, they sound very abstract. And so I wanted to put some more emphasis on what exactly they say and why we should care. And then it turns out that the proof goes through this very abstract machinery of topos theory. And I'll say a couple words about how the proof goes, but I'm not going to go into as many details for how exactly the proof works. If you want some of those details, some simple details about toposes are in the associated notes that will also be on my blog, which I've already submitted to you, Dr. Lapidus.
Yes.
And also the references for that note have an absolutely phenomenal paper by Milne, which is sort of a survey of these topics on how to actually use Cohomology. Okay, so with that out of the way.
Which paper are you referring to?
Here I have it. Here it is. The Riemann hypothesis over fields from Theta to the present day.
Okay.
This whole bibliography is in that paper. So okay, so let's go. So a quick nota bene. I'm an idiot at the best of times, and I am not an expert particularly on this topic, so I will probably make some minor mistakes, but everything I say should be morally correct. Even if I'm an idiot, I'm a well-read idiot, and this talk is going to be an amalgam of a sort of a handful of other talks that I've seen. Notably, you should absolutely look into this talk by Sophie Morel, the Weil conjectures from Abel to Levine, as well as this talk of Colin McClarty, Nevertheless, One Should Learn the Language of Topos. They're both available on YouTube. They're both fantastic. And like I said, there's also references. There's more references to this on my blog as well. So slides are on my blog. That page will also have a paper associated with this talk. And obviously no ideas are my own. This is all very well-trodden territory at this point. See the associated paper for references. Okay, so on with the show. So first of all, what are the Weil conjectures? Let's start there. Let's look at a very concrete problem, okay? Okay. How many solutions to x squared plus y squared equals 1 are there in the finite field fp to the n, right? It's a super concrete problem. Well, when in doubt, this problem is sufficiently concrete that you can just ask a computer. And you can build a table like this. I built this with Sage. And you can see there is some sort of very visible pattern to the number of solutions as we fix a prime and let the power of my prime vary. Notably, the number of solutions, so the number of solutions for the field with 2 to the k elements is precisely 2 to the k. And also the number of elements for p to the k elements for p odd is more or less p to the k. It's within 1 of p to the k. So this is obviously not an accident. And so it's the kind of phenomenon that you might want to study. So why? Well, the answer turns out to be entirely geometric in nature. If we look at x squared plus y squared equals 1, this is a unit circle, citation needed, I guess. And this is a one-dimensional object. Now, why do we care about the fact that this is one-dimensional? Well, we would expect that the solutions should be roughly like the affine line, right? Where by roughly like, you can make this precise with, for instance, birational equivalence, but we won't. And the idea is that the number of solutions should be the same size as the number of points on the affine line, because that's one-dimensional, plus or minus some error term, right? And the Weil conjectures give us a tight bound on this error term. So more generally, if x is some d-dimensional variety, then we would expect the number of solutions in FP to the n to look like d-dimensional affine space plus or minus some error term. Yeah, so, oh, and over FP to the n, there's P to the n affine points. So this is P to the dn many points. And the Weil conjectures are all about controlling this error term. Okay, so with this out of the way, let's introduce some notation. So section 2 is some notation. Let's let x be a family of polynomials with integer coefficients. So we're going to let k be my favorite field. And we're going to write x of k for all of my points in k to the n, which satisfy this polynomial. So if you like, this is never mind. Okay, well, let's let C be my favorite curve, which is the unit circle. Then C of R is precisely.
Assuming your field K is of characteristic. What is a characteristic?
K can be any field at all, right? I'm looking at X as its functor of points, and so I can plug any ring that I want into here.
Okay.
But we are only going to be looking at fields.
Mm-hmm.
So if I plug in the real numbers, I get the real solutions to this equation, which is, of course, just the standard unit circle. If I plug in the rational numbers, I get rational points on the unit circle. And we're interested in counting my FP to the n points on the unit circle. So we're interested in counting C of FP to the n. So these are affine schemes. They're very natural algebraically. Unfortunately, they're less natural geometrically. And because the Weil conjectures are geometric in nature, we want to move to some slightly more natural geometric setting, by which I mean we want to move to a projective setting. These affine curves are missing points at infinity, and it turns out that these missing points are really useful. And not only are they really useful, they're really useful for making counting problems simpler. So it turns out these points at infinity, for instance, if you're trying to count intersections, it turns out you get this very beautiful statement of Bézout's theorem if you work projectively. But if you work not projectively, there's some edge cases that you have to handle that makes the theorem, which is really all about counting, look less nice. So the fact that we're trying to count points tells us that maybe the geometrically natural setting of projective space is going to be the right place to be. So let's say a word about projective space. So now, instead of x being some family of integer polynomials, x is a family of homogeneous integer polynomials, by which I mean if you rescale my inputs, my output gets rescaled by whatever the degree of my polynomial is. Then now what we're going to do is we're going to write x of k for this slightly more complicated looking object, where now I look at all of my non-zero points in k to the n plus 1. I look at the points where they equal 0. Notice this is well defined for an equivalence relation we're about to define because of this homogeneity. And then we quotient out, we say that 2 points are equal if they're rescaled versions of each other. So if you've not seen this construction before, it looks like I pulled it out of a hat. But yeah, I don't know what the experience of everyone in the room with algebraic geometry is, but suffice to say, this is a very natural thing to do. This is the way you go about adding these points at infinity, and I'll sort of leave it there. Trust me that this is not pulled out of a hat. Okay, so it's not as snappy, but these projective schemes add in the points that we're missing. So let's see like a simple example of this. Let's look at the polynomial y minus x squared. So we know intuitively that this carves out a parabola, right? Well, if we were to draw it in perspective, then you could see like this railroad track effect, where as you near infinity, the two parallel lines look like they're actually approaching each other. And in fact, we say that the two parallel lines intersect at infinity. So what does this buy us? This tells it my parabola actually has some bonus point at infinity where my two sort of vertical looking components intersect. So in some sense, it's an ellipse where my point, one side of my ellipse has been moved to infinity. So let's now count the points on C, the projective circle, because that's the more natural thing to do. And of course, we can recover the affine circle from the projective circle. If we know the number of points on the projective circle, just kill my points at infinity. And that's always going to be a lower order term. Since we're dealing with estimates anyways, it won't matter. Okay, so step 1, we homogenize. So that means we take x plus y squared, x squared plus y squared minus 1. We toss in this new variable z squared in order to make this a homogeneous polynomial. Now, we'll count points in the z equals 1 plane, which corresponds to the affine chart that we're used to. And then we'll count points at infinity, which lie in the z equals 0 plane. Again, I don't have time to go over all of the nitty-gritty details of algebraic geometry and how it works, but trust that this is a very natural thing to do, And not only is it a natural thing to do, it's like super computationally effective. So this is something that you really can, if you want to work with these kinds of polynomials, like you can sit down with a sheet of paper and you can actually bash out these computations. And for simple polynomials, it's not too bad. And it's also entirely algorithmic. So even for complicated polynomials, it's still not too bad. You just don't want to do it by hand. You ask a computer to do it for you. And there's all sorts of algorithms for working with these things in Cox, Little, and O'Shea, which is, I think, algorithmic algebraic geometry, or computing with, it's some Cox, Little, O'Shea are the authors. You'll find it. Okay, so the point is, it looks like I'm pulling this out of a hat, but it's really an effective thing to do. Okay, so we'll assume that P is not 2. The P equals 2 case is actually easier than the P is an odd prime case, and it's a cute exercise. Maybe it's worth working out after the talk. Okay, so when z equals 1, we took my, remember, x squared plus y squared equals z squared, and we're now plugging in z equals 1, so we recover just our affine circle. So solving, this means we want y to be plus or minus the square root of 1 minus x squared. Now, in order to solve this, we want to know when this has solutions. That means we want to know when some guy a, which is going to be equal to 1 minus x squared, has a square root in fp to the n. Of course, the question of when a certain value of a finite field has a square root is incredibly well studied. This is basically a theorem due to Euler. So we're going to define this characteristic function, or not characteristic function, a Dirichlet character, from fp to the n to -1, 0, and 1, where a gets into 0 if it's 0, a gets into +1 if it is a square, and a gets into -1 if it's not a square. Okay, so why is this a useful thing to do? Well, it's multiplicative, and we can now use this in order to simplify some calculations. So if we have my points on the unit circle, these are those points where x squared equals a, y squared equals b, and I sum over all of my a plus b equals 1. That's a very easy rewriting of this statement. But doing this, what does it mean for x squared to equal a? Well, you can just check that the definition of this Dirichlet character, that actually ends up being 1 plus chi of a. And 1 plus chi of b tells me the number of square roots of b.
Yeah.
Okay.
So otherwise you get 0.
Sorry?
Yeah, otherwise you get 0 or 1.
Right, exactly. So I've taken this thing that used to be 0, 1, and -1, and by adding 1 to it, I now have 1 when a is 0, because 0 has 1 square root, 2 when a is x squared, because then a has 2 square roots, plus and minus a, or plus or minus x, and 0 if a is not a square. Exactly. So this is properly counting squares. We FOIL this out, we distribute, and we rename b to be 1 minus a, just so that we can be only summing over one variable. Now, the interesting thing is after we distribute the sum, is we notice that these two interior sums are both 0. And why is that? Well, this is actually a theorem we talked about in class. If you take a Dirichlet character and you sum over your entire group, then you end up getting 0. Exactly. And so what we're left with is the number of points on this curve is p to the n plus some error, which is exactly what we were looking for. Now, it turns out in this case, and I've omitted this computation, but again, there's a paper by Robinson which does this out in full. We find that the error term is whatever it's called. It ends up being negative chi of -1. So it's negative and then some thing that depends on whether or not -1 is a perfect square in your field. So points in the z equal 1 plane, or how many points are there in the z equal 1 plane? Well, there's p to the n many points coming from the dominant term, and negative chi of -1 coming from this error term. And we apply this theorem of Euler again, which tells us precisely when -1 is a square. And we can just compute chi of -1 is 1 when p is 1 mod 4, and -1 to the n when p is 3 mod 4. In particular, this is the number of affine points. Okay, so, and you can check, this agrees with our table. So we have this table of values that we calculated earlier. And remember, this table of values was calculating the number of affine points. And you can check that this formula actually agrees with this table. So it's always within 1 of p to the n. And this tells you precisely whether we add or subtract 1. Okay, so what about points at infinity? Well, we set z equals 0. Again, this is a super standard thing to do if you've seen some algebraic geometry. And in the y equals 1 plane, This means we're now looking at x squared plus 1 equals 0, which is x squared equals -1. But we again know precisely when x squared equals -1. It's chi of -1. Okay, so altogether, oh, and there's no points, there's no bonus points in the y equals 0, x equals 1 plane, because as soon as you set y equals 0, you're trying to solve x squared equals 0. The only solution is 0, and that's not a projective point. Okay. So with this together, we know that the number of points on my curve are the number of affine points plus the number of points at infinity. Okay. Well, plugging in for this formula, we find that this is p to the n minus 1 plus 2, because again, there's 2 roots of -1, right? When p is 1 mod 4. And it's the number of affine points was this more complicated thing, plus now 2, but only when n is even, right? Because this is only when n is even, when p is 3 mod 4. And notice that these two guys actually both give me p to the n plus 1. So where we used to have some piecewise definition, now by adding in the points at infinity, we get a uniform definition. So note the simplifying effect when we count the points at infinity. This is sort of a theme throughout all of algebraic geometry. Okay, so we have some family of points, right? Okay, so we have some family of numbers, sorry, where we're trying to count these. And this is, we're thinking of p as fixed and n as a variable. So we have these numbers p to the n plus 1. And of course, for more general curves or more general varieties, we would be interested in counting, progressively more complicated functions. But if you have some sequence of numbers, a very classical idea is to look at the generating function. Now, it turns out we don't use a standard generating function. So I think most people are used to seeing generating functions that look like, for instance, an ordinary generating function or an exponential generating function, or if you've done some number theory, maybe a Dirichlet generating function. But it turns out we don't look at any of those. And I don't really have a good motivation for why we look at this generating function, besides the fact that it works. If anyone has a good a priori justification for looking at this generating function in particular, I would love to hear it. Because it obviously works. And so there should be a reason that you would consider it. But I don't have good justification for what that reason is. But okay, we define the Hasse-Weil zeta function, where we define zeta, where it looks like a z, so we'll call it z, of xt. We're going to take the exponential of this sum. So we take some zeta function, and then we stick it in the exponent, okay? And what's my generating function? Well, it's sort of what you would expect your generating function to be. So it's x, so it's the number of points on fp to the n times t to the n. But we normalize, we divide by n. And again, the reason to do this is because this will end up looking logarithmic. And when we take e to the logarithm, we get something simple. But that's sort of an a posteriori justification. I don't really have a good reason for why you would consider this without knowing that it works. But okay, we'll take it on faith. And why does it work? Well, if we again look at the circle and we compute z of ct, we find this is e to the sum of the number of points here times t to the n on n. But we know how many points there are. There's exactly p to the n plus 1. Now we recognize these guys as power series, and we get that this is negative log of 1 minus pt minus log of 1 minus t. And of course, we're eing that. So we get 1 over 1 minus t times 1 minus pt. Okay, so let's make some observations, and I've rewritten the zeta function in the corner so that we remember it. So observation 1, this is rational, right? So if you give me some arbitrary power series, there's absolutely no reason it should be a rational function of t. But we can write this as p0, p1 in the numerator, p2, where p0 is 1 minus t, p1 is 1, and p2 is 1 minus pt. Now, why I've chosen to write it like this is because it's the version that generalizes. But you can see we can write it in this form, which is interesting. And also notice that 2 is twice the dimension of my curve. Remember, my curve is one-dimensional, and we find that we actually go up to p2, where 2 is twice the dimension of c. That also will end up generalizing. So,
do you want me to explain why you make that choice, or you want to wait until the end, maybe?
If you want to say it now, I would be super interested in hearing it now.
Okay. All right. So, but for that, you have to really introduce the zeta function as of a S of the complex variable S,
Okay.
by a Dirichlet series. So this would be the sum of the norms. As I said very briefly at the end of the course, you take the sum of the norm of the points on your curve to the power minus S, like a Dirichlet series, a standard Dirichlet.
Yeah, like this.
Have it here. Yes, exactly. Oh, this looks like my book, no? Or no?
No, this is my paper actually.
Or your paper.
I say my paper, but this is the thing that I submitted to you. None of the ideas are original. But
Okay.
yeah.
So, okay, now you have the Euler product here. You see, so now in the Euler product, you're going to make a change of variable because the function is periodic. The zeta function is periodic with period 2 pi I over log p or log q more generally, if q is p to the m, but p to the n. So you make the change of variable, let's say key equals u to the q to the minus s. So q is p to the n, or not that p. Are you working just in characteristic p, but I mean over a field of sorry, you're working over fp, not fq.
Why does it keep throwing me back here?
I don't know.
I don't know either.
Yeah.
Well, okay. Regardless.
Okay, so let's make the change of variable u equals p to the minus s. Then your function becomes 1 minus, I mean, your Euler product becomes, as an expression like product of 1 minus t to the power something to inverse. And okay, if you call this function w of t, you take its logarithmic derivative, you find a power series, which involves the nu sub n. I mean, how did you call your number, your counting points?
I just calling it this. I guess if you want to call it n.
Yeah, I call it nu sub n or something.
Yeah, sure.
So you obtain, so this function becomes a power series, which is like sum of nu sub n t to the n minus 1. And then so that's the logarithmic, that's the logarithmic derivative of the function, which you obtain once you take the Euler product and you make the change of variable t equals p to the minus s. And now, so you just integrate, because that's the logarithmic derivative, so it's the derivative of the log of that function w. And so that's sum of nu sub n over n u to the minus u to the n, so or t to the n. That's how you get this 1 over n here, and that's nu sub n. So this is and now, so this was the log of your function. So you exponentiate, and that's how you get the left hand side. I mean, it'd be easier if I could write it.
Yeah, of course.
But this is exactly where it comes from, the Euler product, and then the periodicity in the s variable, and so which gives you the idea of making the change of variable u equals p to the minus s. So more generally, q to the minus s if you work over a finite field fq instead of fp, and then you go through. You just take the logarithmic derivative of that function that you get a power series. You integrate, so you integrate, you get the log of that function, and then you exponentiate, and you get the exponential of that expression that you have.
Yeah. Do you know, is that all written down somewhere in Search for the Riemann zeros?
Yeah, it's written in Appendix B. Appendix
B, perfect.
On page 3, I mean, you should start earlier to see what the notations are, but it says 329, 330, 331.
Okay.
It's of course well known, but yeah, you can see it there, 329 to 339, 331. You can almost read them, like self-contained, that part, more or less.
Yeah.
And
great, thank you.
Yeah. It's not coming out of nowhere.
No, of course.
Natural.
Yeah. If you're purely thinking of this combinatorially, though, as trying to count these sequences, then it feels like it's pulled out of a hat. But of course, I guess it comes from the some slightly deeper structure.
Yeah, just the Euler product and Dirichlet series, which gives rise to the Euler product, and then you make the change of variable due to periodicity.
So, okay. So the first observation is that this zeta function is rational. And again, the number of polynomials has to do with the dimension. Okay. Now, moreover, we know that each of my polynomials factors over the complex numbers. It's some integer polynomial. I can factor it. Yeah. And when I factor it, it looks like this nice normalized form. And each of my coefficients on t has norm p to the k over 2, which is really interesting. And this is, or I guess I'll say that this is called the Riemann hypothesis later, but this is the Riemann hypothesis because it tells you precisely where the zeros of my zeta function are, right? Okay, so next there's a functional equation. So if I plug in z of 1 over pt, this corresponds, or this equals pt squared times z of t. And moreover, the 2 here is not an accident. The 2 in the t squared is, well, if I look at my complex points, then my complex points form a sphere. And it's well known that the Euler characteristic of a sphere is 2. And so this 2 is actually the Euler characteristic of a sphere. And speaking of the fact that the complex points form a sphere, notice, and this is now beginning to really stretch, the degree of P0, so remember P0 was 1 minus t, P1 was 1, and P2 is 1 minus pt. So the degree of P0 is 1, which is the dimension of the 0th cohomology group of the sphere. The degree of P1 is 0, which is the dimension of the first cohomology group. And the degree of P2 is 1, is the dimension of the second cohomology group. So somehow, and the fact that I'm writing this down means that it's not an accident, of course. So somehow the dimension of the cohomology groups of the complex manifold associated to this polynomial tells me the degree of the relevant functions that are showing up inside this zeta function. There's a thing in chat. Alternative way of, oh, very cool. Okay. Okay. So with this out of the way, really, what are the Weil conjectures? So let X be a smooth, projective, n-dimensional variety over the algebraic closure of Fp, whatever that means. And in fact, we're going to assume something slightly nicer than this. We're going to assume that this is actually the mod p reduction of some smooth, projective, n-dimensional variety over the complex numbers. And that greases the wheels a little bit. It makes the Betty numbers claim true. It makes part 4 true. But you can get by in some slight more generality. So what do I mean for it to be smooth? Well, I mean that the Jacobian has full rank at each point. So when I define varieties, I said that you were allowed to have infinitely many polynomials. It's of course a theorem that finitely many always suffices. And so you look at the Jacobian and you say, does it have full rank? That's a reasonable definition of smooth. Projective we've already talked about, and n-dimensional. Okay, the algebraic notion of dimension is a little bit subtle, but you know, it means what you think it means intuitively. So they made the following conjectures, which are now theorems. They've all been proven about z of xt. So 1, it's always rational. And remember, n is the dimension of my complex manifold. And we find that it always looks like this, with sort of odd polynomials upstairs and even polynomials downstairs. We'll see why we index them like this when we get to part 4, where each pk is an integer polynomial in t. And moreover, p0 is always 1 minus t, and p2n is always 1 minus p to the nt. Remember, n is the dimension of my variety. So 2, and this is called the Riemann hypothesis, each pk factors in the same way that we saw things factor for the circle. And moreover, the sort of root of, for the kth polynomial, these roots occur with norm p to the k over 2. Okay. We have a functional equation. So 1 over p to the nt, if we plug that in, that's the same thing as up to sign, p to the n times the Euler characteristic on 2 times t to the Euler characteristic times my original zeta function. And of course, lastly, the degree of pk, sorry.
Chris, yes, keep this for a second. So you see when you make the change of variable like t equals u to the, sorry. T equals P to the minus S here,
Mhm.
then this corresponds to the usual symmetry S and
Yes.
minus S.
But this corresponds to
minus
the
n.
symmetry for the completed zeta function, right?
Yes,
Yes.
but and it becomes S and n minus S.
Yeah, I wrote something like this in the paper that again you can find on my blog, or Lapidus, I sent it to you, where somehow, because this looks like the completed zeta function, and if you run this same argument, you can run a similar argument for affine curves rather than projective curves. It turns out the standard zeta function looks more like an affine curve than a projective curve. And so in some squishy sense, the Riemann hypothesis is about looking for some notion of a projectivization of spec C. And we know roughly what that should look like. We should pick up these factors of, depending on your convention, some power of pi times the gamma function. But as far as I know, we don't really have a good justification for where those things should come from geometrically. And again, in my paper, I cite some survey article, which talks about some possible ways of attacking the Riemann hypothesis that talks about this. It's really, really interesting. I know so little about it, I've already probably said too much. But it's really interesting stuff.
Yeah, it's good that you're humble.
Okay. So lastly, we have the degree of pk, and this is the dimension, the kth cohomology group of my variety with coefficients in Q, where H dot is exactly the cohomology, right? Okay. So this is really interesting, because notice we have this constant interplay between, on the one hand, algebraic properties of the zeta function. And remember, the zeta function is somehow controlling the size of roots, right, of solutions to this equation, mod p to the n. And so we have this interplay between algebraic properties on the one side and geometric properties of not just like this scheme theoretically of X, but in particular viewing the complex points as a complex manifold and using some like continuous manifold theory in order to compute, for instance, Euler characteristics and Betti numbers and things like this. So, right, we have this interplay between the generating function and some sort of complex manifold. And this is magical and obviously shows that you're on the cusp of something very profound. But at a very concrete level, how do we use this, right? We have this very deep and beautiful connection, and I'm personally of the opinion that anything which is beautiful in mathematics probably is useful as well. And so let's just ask a very simple question. How many solutions are there to this polynomial in 6 variables over fp to the n? Right? It's a very simple question. And the answer is we recognize this polynomial as a slightly obfuscated version of the Plücker embedding of the Grassmannians into the projective space P5. And if you don't know what this means, don't worry about it. It just means that the geometry of the complex solutions of this is incredibly well understood. In fact, everything that I'm about to say, you can type Grassmannian into Wikipedia and you'll get everything that I'm about to say. So first of all, we know that the dimension is 8. We know that the cohomological stuff, the dimension as a complex space is 4. The dimension as a real space is 8. The cohomology is 0 when n is odd, 2 when n is 4, and 1 when n is even but not 4. And we know its Euler characteristic is 6, which happens to be 4 choose 2 for the interested. And again, this is all on the Wikipedia page for Grassmannian. Yeah, you can see I've switched from the dimension is 8 because that's real dimensions. We're actually interested in 4, which is the complex dimension. I clearly wrote these slides a bit late. Okay, but so z of t, then what does this tell us? Well, we know it looks like some polynomials, right? Well, all of my odd degree polynomials, right, have degree 0. So the odd cohomology groups are 0. And remember, the odd things are precisely the numerator. So we only get degree 0 polynomials in the numerator. Down here, we have my even degree polynomials. And we can read those off of here. So we got this, we get the degrees of my even polynomials. And let's write these, let's factor them over the complex numbers as 1 minus alpha 2, 1 minus alpha 4, 1, and 1 minus alpha 4, 2, because that's degree 2 polynomial, and 1 minus alpha 6. If we hit both sides of this with log and we Taylor expand, then on the left-hand side, remember, log of my zeta function is exactly this thing which counts the number of points. And on the right-hand side, we can, when we hit this with log, right, this product becomes a sum, and we get, you can just Taylor expand it, and we see this. And notice, by the Riemann hypothesis, each of these, well, the Riemann hypothesis for varieties, right, this part 2 of the Weil conjectures, we actually know what the norm of these AKs are. So this gives us asymptotic control over the number of points. And if we had decided to calculate the AK precisely, which you can do, I just didn't, that's an effective operation, then we can actually know the exact answer for the number of points on this variety. And it looks kind of bad at first blush that, you get p to the 4n plus or minus big O of p to the 3n many points. 3 because 6 divided by 2 is 3. Okay. And that's the biggest of these error terms. So that looks bad at first blush, but if you factor out a p to the 4n, then this is telling you, right? I think Will was talking about this in an earlier talk, where the difference between additive and multiplicative error bounds. The additive error bound is quite bad, but multiplicatively, this is telling me there's actually a quite good error bound if you factor out a p to the 4n. Okay. So how do we prove this, right? So we know that somehow, just by understanding the geometry of this of these Grassmannians, we get very tight control over the number of points or the number of solutions to this polynomial equation mod p to the n. This is super interesting. It would be really nice if we knew that it was true. Well, here's a proof in quotations, because you have to suspend your disbelief a little bit. Recall fp to the n are precisely, if I look at the algebraic closure, it's exactly the fixed points under phi to the n, where phi is the Frobenius map. And this is basically a theorem in Galois theory. So we want to count the fixed points of phi to the n from this variety to itself. Okay, well, we're now going to pretend that my variety really is a geometric object. So I have geometric tools available to me. Well, if I have an endomorphism of some manifold and I want to count its fixed points, well, you hit it with the Lefschetz fixed point theorem. So the Lefschetz fixed point theorem, if we just sort of formally apply it and pretend that everything works, then we see that the number of fixed points of f is exactly this alternating sum of the trace of f on the kth cohomology group. Okay, which again, these are all things that you can actually calculate if you need to. So for us, this here, the number of points in fp to the n, is exactly the alternating sum of the trace of phi to the n on this cohomology group. Okay, and if we hit this with exp, then this sum becomes a product, and traces turn into determinants. And it's a really quick exercise to see that we find that zeta of xt is the product of the odd things, right? This alternating sum tells me whether I end up in the numerator or the denominator. I get my odd determinants upstairs, and I get my even determinants downstairs. But if I define my kth polynomial to be this determinant, remember this is just like the characteristic polynomial, then we get exactly the rationality. And in fact, more geometric properties continue to imply these. So statement 3, the functional equation, is more or less Poincare duality. Statement 4, so the idea that the degrees of these polynomials should be the Betti numbers, is roughly the definition of the Betti numbers. That's because the degree of the characteristic polynomial is just the dimension of your vector space. And 2 is trickier. It follows from a theorem of Serre, and that's all I know about it. I don't actually know what theorem of Serre, but this was mentioned in this talk that I mentioned of Sophie Morel. Okay, and it turns out that the fact that this is trickier and relies on some theorem of Serre turns out to be really important to the history of the proofs of the Weil conjectures, because these two are both sort of obvious corollaries of how we expect cohomology to behave. The fact that 2 depends on a trickier theorem tells you that it doesn't follow formally. And we're going to talk a little bit more about that. And that's why Deligne had to prove this sort of by hand. Okay.
So Chris, by 2, you mean the alpha k?
Yes.
The factorization in terms of alpha k being the algebraic numbers. You didn't mention alpha k are algebraic numbers, or did you?
No, I didn't mention. So I guess that's a thing worth mentioning. So the alpha k, not only are they algebraic numbers, but they're very special algebraic numbers.
Yeah.
Right? Because I sort of glossed over this, so it's probably for the best that you brought it up. But the norm of an algebraic number, right, the size of the complex norm of an algebraic number is not actually well defined, right? If you look at like 1 plus the square root of 2 and 1 minus the square root of 2, as far as algebra is concerned, these are the same. There's a Galois action that swaps them, but they have different norms in the complex numbers. And so the alphas that show up as roots of these polynomials are actually particularly special algebraic numbers. They're algebraic numbers where no matter which embedding into the complex numbers you pick, they have the same norm. So I think these are called, are they Weil divisors? What are they called?
Yeah, I think so. But yeah, so true, they have the same norm.
So yeah, they're particularly special algebraic numbers. These
but this is what you were referring to for part 2, right? That's for 2.
Yes, for part 2, I'm referring to the fact that the norm of these alphas is exactly p to the k over 2.
Yeah. But that's the Riemann.
Yes, which is the Riemann
hypothesis.
Exactly. And the idea here is that there's a theorem of Serre, something to do with Turing classes that I'm not going to pretend to understand, that sort of formally tells you what the norms of these roots should be.
Oh, yeah, formally, but it wasn't proving the
right. No, but it was not proven that way. Yes, I'm going to mention later that Grothendieck has these standard conjectures, which if you're able to prove the standard conjectures, then you would be able to sort of formally get the Riemann hypothesis. But no one has been able to do that. They've been open for a very long time, all but one, I think. So yeah, really interesting stuff. Okay, of course, this proof can't work. And why? Because this isn't actually a manifold. Yeah, we use geometric language to talk about it, but we're sort of cheating when we do that, right? So there's no cohomology theory for it, unless section 4, in which we show there is a cohomology theory for it. So now we're going to get into the topos theoretic aspect of this talk, because it turns out that constructing a cohomology theory for this, in order to make this informal argument work, requires some incredibly high power machinery. And this is now going to be, yeah, this is going to get a little bit squishier, if you can even imagine such a thing, because I don't have time to go into a lot of the details here. This is going to be like very high power, not only topos theory, but homological algebra. And we're already assuming some algebraic geometry, and you know, I'll say words as they arise. Oh, there's something in chat. You have to leave. Yeah. Okay, cool. So in his Tohoku paper, Grothendieck found an axiomatic framework for cohomology theories. There was sort of a zoo of cohomology theories floating around, and Grothendieck showed that they're all sort of different flavors of this cohomology theory based on abelian categories. So he defined these things called abelian categories. He showed how to get a cohomology theory for any left exact additive functor between two abelian categories A and B. Provided, and this is a little technical aside, A has enough injectives. That's some technical requirements that we're going to note, but we're not going to say a ton about why injectivity or why having enough injectives gives you cohomology theory. But if you want to, you can feel free to ask me about it after the talk. And he showed that any abelian category satisfying this axiom that he called AB5, and it has to have a generator, but okay. AB5 is the really important condition. If you have AB5, then you automatically have enough injectives. And again, he showed this axiomatically. So instead of having to work with as an ad hoc basis, if you can show that you're in a abelian category and you have AB5, then you satisfy AB5, you automatically have enough injectives. And then once you have enough injectives, you automatically have a nice cohomology theory for any left exact additive functor. Okay. He also showed that for any space X, the category of sheaves of abelian groups on X satisfies AB5. So why is this useful? Because you recover, if you look at the cohomology of the global sections functor, you get classical sheaf cohomology when you run through his sort of axiomatic treatment. And nowadays, this is how we, or how a lot of books define sheaf cohomology. Okay, so Serre, in a talk, found a way to build a notion of the first cohomology group using these things called unramified covers. And Grothendieck, perhaps optimistically, knows that covers and sheaves are equivalent. And where there's sheaves, there's an AB5 category. And where there's an AB5 category, there's cohomology. So Grothendieck, after this talk, tells Serre, and now I'm recounting a story that Colin McClarty gave in the talk that I cited at the top of this talk. Apparently, Grothendieck went up to Serre after this talk and said, "Yeah, that's going to work in all dimensions." And Serre basically said he knew how hard he had worked to prove it for the H1 case, and he said, "You're being a little bit ambitious," but it ended up working out. So, what's the idea? We redo this sheaf theoretic stuff in a more general setting, giving us a more general notion of sheaves, which ideally should still share enough of the properties of sheaves on a topological space to let us redo the proof that sheaves of abelian groups satisfy AB5. But once we do that, we profit. We get a cohomology theory for these generalized sheaves, and ideally, we would be able to massage this machinery in order to make it work for to build what's called a Weil cohomology theory. Okay, so recall a sheaf on a topological space x tau is a function taking open sets of my topological space to sets so that I have a nice restriction mapping and some covering condition. So if I have an open cover of an open set, and I have a section defined on each patch of my open cover, and they're compatible in the sense that they agree on intersections, then there's a unique way to glue these sections together into a section on my entirety of U. Okay, so as a cute example that I'm legally required to give, let's say f of U is the set of continuous functions, continuous real valued functions on U. Then if I have an open cover of U, so restriction is just literal restriction of functions. And if you give me an open cover and you give me a function defined everywhere on the open cover, and my functions agree on the overlaps, then I can stitch those together and get a function defined on all of U. So here's a picture. This white circle is U. All of these purple circles are my open cover. And if you give me a point in the if you give me a point over here, I just do f alpha. And if you give me a point in the intersection of f alpha and f beta, then it doesn't matter which one I choose because f alpha and f beta agree here. So there's sort of a canonical way to do this. Sorry, there was a question?
No, I was just pointing out, of course, their function is unique.
Yes, and the function is unique. Yes. Okay. So to define sheaves, what do we really use? Well, we need a notion of open sets. We need to know when some family of open sets covers another open set. And we need to know what it means for two of these open sets to overlap. Okay. So you might think, well, open sets, we can sort of do whatever we want with those. That's just going to be our objects of interest. So let's just look at a category. And then we're going to put some structure on a category to say when a family of objects covers another object. And you can think about that being as a kind of co-limit condition, because co-limits are like unions and covering is like taking a union. And we want to know when two of these guys overlap. And you can think about that as being a limit condition because the intersection is a pullback. Okay, so definition. If C is a small category, we can declare what's called a Grothendieck topology on C. It's a choice of JU. So if U is an object of C, I'm calling it U for analogy with open sets, then J of U, we pick subfunctors of the representable. We call this covering, we call the subfunctors that we choose, we call them covering families, and they satisfy some natural coherence conditions. Now, if you're not familiar with subfunctors, or if you want to know what these coherence conditions are, please ask me after the talk. I also say more in the fully written out version of all this, but we're already running a little bit long. Then, imitating the classical definition, we can define a sheaf on this category to be a functor from C op to set, so that whenever I have some covering family, if I have a natural transformation from my covering family to my sheaf, then that actually extends to a natural transformation from my representable to my sheaf. And if you think about what this means, right? Do I say something? Yeah. So the Uneta lemma tells me that natural transformations from my representable to my sheaf correspond exactly to points of my sheaf. And if you think about R as being a family of objects mapping to U, so a very good piece of intuition to have is work through this machinery when C is a poset. Then the fact that R is covering sort of tells me that I have a bunch of objects, all of which see U. So you can imagine if I have like a mono into U, you can think about that as being like a sub-object of U. And I have some covering family. So I know that these subobjects in whatever sense cover U. And so the fact that I can view this guy as some collection of representables, indeed, every pre-sheaf is a colimit of representables, tells me that somehow I'm saying if I have a thing defined here on this colimit of representables, and it's coherent, so it agrees in a very natural sense, then I can extend it to something defined on the whole of U. Okay, where again, I'm glossing over a lot of details here because it gets quite technical quite quickly. But we can now define this sheaf category, where if I have what's called a site, so a small category equipped with a topology, I can define sheaves on this site to be, sort of the natural thing. It's just the category of sheaves as defined here, equipped with natural transformations as their arrows. And definition, a category equivalent to sheaves on site is called a Grothendieck topos or Grothendieck topos. So then again, I'm sort of powering through everything here because I knew as I was writing these slides that it was going to be a long talk. So we can define the category of abelian groups in E, written ab E. And the way we do this is you literally just run the argument for what an abelian group is in set, right? So an abelian group in set, you have a group or you have a set, you have a function from A times A to itself called multiplication. You have a function from A to itself called inverse. You have a function, you have a point in A, which is a function from the terminal object to A. And, if you've seen any categorical logic, it's sort of obvious what to do here. But you have to reframe what it means to be an abelian group in a very natural way. You sort of write the axioms as commutative diagrams. And again, if you want to talk to me about this, feel free. I also include a much more explicit description in the paper on my blog. So the same argument from Tohoku shows that the category of abelian groups inside of E satisfies AB5. So if you look at all of my abelian group objects inside my category, that forms itself a category. And the same argument from Tohoku that showed that the category of abelian groups of sheaves satisfies AB5 shows that this category also satisfies AB5. Is there another question?
No, I don't.
Okay, cool. I thought I heard something. Sorry.
Yeah, that was my chair. Let me remove.
Okay, no worries. But what do we do when we have this? Then the global sections functor, which is the map from the terminal object, becomes a left exact additive functor, which takes a sheaf of abelian groups, where now I mean sheaf in this more general sense, and spits out a regular abelian group. So what do we know about I have a left exact additive functor out of some AB5 category? It has a natural cohomology theory. Just look at the right derived functors. So in fact, it's exactly this cohomology that solves the Weil conjectures, just as Grothendieck predicted. So let's see just an itty bitty bit more. I knew as I was writing this that this was going to be a long talk, so my apologies. But here is the general sketch of how you do this. We write etal over X for the category whose objects are etal maps, where I'm not going to try to say what an etal map is, but if you know, you know. And the arrows are going to be maps between two etal coverings, making the diagram commute. So you can think about these as being covering spaces with covering space maps. It's sort of an entirely analogous phenomenon. If you're familiar with slice categories, that's why I chose this notation. And now we say that a family of etal maps from U alpha to U covers U, where I'm doing the thing that we always do with slice categories, where I identify an arrow into X with just the domain, because life is too short to write this all the time. So I say that this covers U exactly when it covers U. So if I look at the images of U alpha of all these etal maps, the union should actually be all of U. And it turns out that it's a very simple check to show that this is a Grothendieck topology on the etal spaces over X. Now, the resulting cohomology theory is enough like classical cohomology for the proofs of 1, 3, and 4 to go through pretty much unchanged. You have to show that the cohomology theory behaves like this, but you can do that. But interestingly, not the Riemann hypothesis. So this had to be proved separately by Deligne, although of course the ideas of this cohomology theory and toposes are implicit in Deligne's proof. He just found what Grothendieck considered to be a trick, which I think Grothendieck uses in a more pejorative way than I'm using it here. And Interestingly, there's a set of
He
so-called
was
standard-
very upset at the view for some reason.
Yeah, he felt really betrayed that that I mean the theorem got proved, right? Like you should be a static. But
Yeah.
okay,
He
regardless.
wasn't. I don't think he was.
Yeah. So there's a set of standard conjectures, which, if true, would allow us to formally recover the Riemann hypothesis in the sort of similar way that we were able to formally recover the other parts of the Weil conjectures. Unfortunately, almost all of these conjectures are wide open. So, you know, if you've got some free time and you really want a Fields medal, maybe give them a shot. All right. Thank you. That's all I have. I know I went a little bit long, but yeah, there was a lot to say.
Thank you very much. A very nice talk. So